Welcome all for the lecture on optical isomerism. Before discussing about optical isomers, we shall have a brief introduction for stereochemistry. Stereochemistry is the branch of chemistry which deals with the spatial arrangement of atoms and groups in a molecule and its relation to the properties of the molecule. Isomers. What are isomers? The different compounds with the same molecular formula are called isomers. The concept of different molecules existing with the same molecular formula is known as isomerism. Now we shall see how isomers are classified. Let us consider we have two molecules A and B. If they are having the same molecular formula, then they are isomers. And if these isomers are having the same connectivity of atoms, then they are stereoisomers. If they have some difference in the connectivity of atoms, then they are structural isomers, and there are different types of structural isomers like functional isomers, positional isomers, and chain isomers. Now, if the isomers are having the same connectivity of atoms, and if they differ only in the spatial arrangement of atoms and groups in the three-dimensional space, then they are called stereoisomers. And if these stereoisomers are interconvertible by a rotation about carbon-carbon single bond, then they are called conformational isomers. If they are not interconvertible by rotation about carbon-carbon single bond, then they are called configurational isomers. And if the configurational isomerism is due to a restricted rotation about carbon-carbon double bond, then those isomers are called geometrical isomers. And if there is no restricted rotation, then such configurational isomers are called optical isomers. And if these isomers are the mirror images of each other, which are non-superimposable on each other, then they are called enantiomers. And the isomers which are not the mirror images are called diastereomers. So, the optical isomers, which are being the non-superimposable mirror images, are called enantiomers or optical isomers. Isomers, which are non-superimposable mirror images of each other, are called enantiomers, and this kind of isomerism exhibited by isomers or the enantiomers is known as enantiomerism or optical isomerism. And these enantiomers, let us see these two molecules A and B. These are the mirror images. Let us consider this as the mirror. A and B are the mirror images of each other. Now, you just take this molecule out from the plane and just try to put it on the molecule B. Now, when you place the molecule A on B, R4 will be eclipsing with R2, and we will get R2 above this R4. So the similar groups are not exactly matching with each other, and that is what we call as non-superimposability. So these two molecules, which are the mirror images and not being superimposable, are called enantiomers. Optical isomerism arises from the non-superimposability or chirality, which is otherwise called handedness. If we just look at our two hands, they are just looking at like the mirror images, and if we keep one hand on the other, they are not exactly matching with each other. That is called handedness. and such a property is called chirality or non-superimposability. So the enantiomers are non-superimposable and hence they are called chiral molecules. And these chiral molecules, the enantiomers, interact with the plane polarized light and rotate the plane of the plane polarized light in the clockwise direction or in the anti-clockwise direction. So the enantiomers which are rotating the plane of the plane polarized light in the clockwise direction are called dextrorotatory isomers, and those who are rotating the plane of the plane polarized light in the anti-clockwise direction are called levorotatory isomers. Dextrorotatory isomers are denoted or represented with a prefix d, small d, or plus, and the levorotatory isomers are represented with small l or minus. So these enantiomers, these molecules which are capable of rotating the plane of the plane polarized light are called optically active molecules. What is plane polarized light? The ordinary light, monochromatic light, propagates through different planes which are perpendicular to the axis of propagation. When this normal light, which propagates through different planes, when allowed to pass through a polarizer, usually a nickel prism which is made up of calcite, it allows the light which travels through one plane alone. So the light that comes out from this polarizer will propagate only through one particular plane. So this polarizer is just like a slit which blocks all the lights which are traveling through different planes other than the light that travels through this particular plane. And this light is called plane polarized light. When this plane polarized light is allowed to pass through a sample of organic compound, a chiral compound, this chiral organic compound interacts with the plane of the plane polarized light and rotate the plane of the plane polarized light either in the clockwise direction or in the anti-clockwise direction. So the plane polarized light is allowed to pass through the sample which is a solution of organic compound. So this chiral organic compound interacts with the plane polarized light and rotates the plane of the plane polarized light. So the angle to which the plane of the plane polarized light is rotated is called optical rotation or angle of rotation. Therefore, for a molecule to be optically active, it has to be chiral. So what are the conditions for a molecule to be chiral or to have chirality? In 1874, Van 't Hoff proposed a theory. The two most important postulates of his theory have formed the basis for most of our organic chemistry. One is a carbon atom which is attached to four groups. A carbon with four attachments is always having a tetrahedral geometry. So a sp3 carbon with four different bonds is having tetrahedral shape. A molecule having a tetrahedral carbon with four different groups may exist as a pair of isomers which are the mirror images of each other, and they are the enantiomers. So these are the two most important postulates of this Van 't Hoff theory. A carbon atom which is bonded to 4 different groups is called chiral carbon or asymmetric carbon or stereocenter or chiral center. And the molecules which are having this asymmetric or chiral carbon are considered as chiral molecules. They are considered, they are believed to have the handedness. So we have given the 2 enantiomers of lactic acid here. So here in lactic acid, a carbon is connected to 4 different groups, and these 2 are the mirror images and these are enantiomers. And these enantiomers are chiral. This molecule is chiral and this enantiomer also is chiral. And these chiral molecules, these asymmetric molecules can interact with the plane of the plane polarized light and can rotate the plane of the plane polarized light. That's why these molecules are said to be optically active. So far we have seen chirality is the essential condition for a molecule to be optically active. Chirality. Chirality is the essential condition for a molecule to be optically active. What is chirality? Handedness is called chirality. Now you see these 2 hands are looking like mirror images, but if you lift this hand and put it on the other one, they are not exactly matching. The gloves that you are using for right hand will not suit for left hand. That is called the handedness or non-superimposable nature. So the right and left hand are looking like the mirror images of each other, but these 2 are different objects. Just like that, the mirror object is always different from the original object, and this is applicable for all molecules. The enantiomers are different from one another, or they are different molecules. So in the earlier days, the presence of asymmetric carbon in a molecule was called as chirality. The presence of asymmetric carbon was considered as essential for a molecule to be optically active. So chirality is essential for the optical activity of a molecule. If chirality is only the presence of an asymmetric carbon, all the molecules with asymmetric carbons should be chiral and should be optically active. So a molecule with asymmetric carbon, it was assumed as chiral, was considered as chiral, and for a molecule to be optically active it should be chiral. In that case, all the molecules containing asymmetric carbon atoms should be chiral and they should be optically active. But let us consider this molecule, mesotartaric acid. It has 2 chiral atoms, 2 asymmetric carbon atoms or stereocenters, chiral centers. But still it is optically inactive. Therefore, the mere presence of asymmetric carbon is not enough for a molecule to be chiral or to be optically active. Therefore, now we have to think about changing the conditions for chirality. So far we had been thinking like the very presence of asymmetric carbon gives chirality for a molecule. But we have seen tartaric acid with 2 asymmetric carbon atoms is achiral. The molecules which are not chiral are called achiral molecules. So tartaric acid, mesotartaric acid with 2 chiral centers, 2 asymmetric centers is achiral. So we have to revise the conditions for chirality. For a molecule to be chiral, it is not enough if it possesses asymmetric carbon atoms alone. Instead, the whole molecule should be asymmetric. So what is meant by the molecule being asymmetric? The molecule should not possess any of the following symmetric elements. For a molecule to be asymmetric, it should not possess plane of symmetry, inversion center, proper axis of rotation, or improper axis of rotation. A molecule which does not possess these four symmetry elements is called asymmetric molecule. Now